In the last lecture we discussed about different types and different kinds of uncertainties. We also said that the second and third kind of uncertainty mostly associated with the mathematical modeling errors, and the other one can be easily handled using what we call as a Bayesian approach. So, what we can make an important statement in this lecture, which is a continuation of the last lecture, is that reliability studies or reliability methods are generally circumscribed by probability methods. On the other hand, probabilistic tools are used to carry out reliability analysis. We all know the answer for this question, but still try to answer this, because probabilistic tools or probability tools can handle uncertainties logically, okay, in a logic manner. They are capable of handling uncertainties in a very logic manner. Therefore, generally reliability methods are circumscribed using probability tools. Now, we have seen two types of uncertainties. One is arising from the randomness in nature, which is arbitrary type. The other is from the modeling methods or analysis tools, which is an epistemic type. Now, there are different groups, that is, the types of uncertainties can be grouped. They can be grouped. Group 1, group 2 and group 3. There are 3 groups. Group 1 deals with uncertainties associated or arise from those arise from material characteristics like Young's modulus of the material, modulus of elasticity, etc. Poisson's ratio, which are all purely material characteristics, they are grouped as 1. The second group are associated with uncertainties that arise from load effects. The moment I say load effects, I have got 2 kinds again. One is static, other is dynamic. I can give examples of static: dead load, imposed load, what we call as a live load, payload on the top side of the platform, etc. Dynamic: earthquake forces, waves, etc. Now, the uncertainties associated with the dynamic forces or the load effects caused by dynamic forces are much more than that of static. That is one comparison between these two. Further, the uncertainties associated with group 2 are much larger than that of material. So, one should focus more on uncertainties from group 2, it is expected. But interestingly, group 1 and group 2 are combined. Very interesting and very salient and very valid example is that if you look at one of the characteristics of the material, which is Young's modulus, if you study Young's modulus in static state of loading, it is different. If you study Young's modulus in dynamic state of loading, it is different. Okay. Whereas dynamics and static form group 2 of uncertainty, variation of E itself is in group 1. So, these two are linked. It means in a given type of uncertainty, there are no Harline differences between the groups of uncertainties, they can loop over the other also. Okay. The third group of uncertainty mathematical modeling, they arise from mathematical modeling and analysis methods. Why? Because each method of analysis has certain set of assumptions or structural idealizations which are reasons for this group of uncertainty. So, let us quickly highlight what would be the effect of group 2 on 1. Let us talk about Young's modulus dynamic or modulus of elasticity or dynamic modulus of elasticity. It is nothing but the ratio of stress and strain under vibratory conditions. They are generally obtained during the free vibration or forced vibration test conducted on loads applied like shear, tension, compression, etc. Dynamic modulus of elasticity is a property of viscoelastic material. Whereas static modulus of elasticity is a property of elastic material. If the material is purely elastic, then there will be no lag between stress and strain. What does it mean? If stress is the applied action and strain is the reaction or deformation or response of the material, then in case of elastic materials, the action and response occurs or occur simultaneously. There is no lag. But in case of viscoelastic material, there is always a lag between the strain and the stress. Usually strain lags behind by pi/2 radians. So, they are out of phase by 90 degrees. Okay. The strain will not occur at the maximum point where the stress is occurring in the same phase, can be shifted by 90 degrees, that is a property in viscoelastic materials. So, strain can be sin omega t, whereas stress can be phi. It is an advanced state. Equation number 1. More interestingly, modulus of elasticity, which is simply E, describes stress strain behavior under monotonic loading. Whereas dynamic modulus of elasticity, indicated by E dynamic, describes stress strain behavior under cyclic or vibratory loading. If you look at the research conducted by people in the recent past, people have conducted modulus of elasticity, observed, assessed on the same material on different specimens and different loading patterns. They did not show the same behavior. Okay. Very interesting reference. There is a very interesting report given by Popovics et al. In 2008 explaining the difference between the characteristics of modulus of elasticity and dynamic modulus of elasticity on a specific material concrete and a different. So, he has listed that various factors which influence dynamic modulus of elasticity of concrete as a material or for any material in general are the following. E dynamic measured on the basis of pulse wave propagation. Or higher. Compared to resonance vibration measurements. So, method by which you are estimating the E dynamic is also one important factor which influences the modulus of elasticity. So, there are two techniques by which one can find out. One is a simple forced or free vibration under the resonance condition, other is what we call pulse wave propagation technique. Okay. So, both give different dynamic modulus of elasticity conducted on the same specimen on the same material. 2. Dynamic modulus of elasticity computed on prismatic sections like for example rectangular, square, etc. are higher compared to that of cylindrical specimens. And they also said that dynamic modulus of elasticity depends on the material on which it is conducted. So, one can say the factors influencing dynamic modulus of elasticity could be shape of the specimen taken for the test, method of assessment, whether you are using pulse wave propagation technique or using forced simple free vibration method on resonance condition, etc. 2 of 3 could be of course the material characteristic itself. So, I will give you some relationship established by different researchers on computing dynamic modulus of elasticity. So, let us say E dynamic based on longitudinal vibration frequency this is based on ASTM C215 technique. There are certain assumptions for this experiment conducted. It is one dimensional, The other is it is a plane section motion. There is no distortion being invoked in the material. Says E dynamic can be given by Vp square rho equation number 2, where Vp is the pulse wave velocity, rho mass density, mu Poisson's ratio of the material. So, using this equation I can find out dynamic modulus of elasticity if I know for varying of a various pulse velocity waves. The other method is using two frequency technique given by Lau 1994 and Subramaniam et al. 2000. Lau AEH 1994 Mathematical Theory of Elasticity, Dover's publication, New York, Subramanian, Popovics, determining elastic properties of concrete is J.P. Shah. Let me write it. Determining elastic properties of concrete using vibration resonance frequencies of concrete cylinders. Cement concrete, cement, concrete and aggregates, ASM, (22) to 82-89. It is 81-89. according to this technique, two frequencies have been used, which first identifies the dynamic Poisson's ratio, then based on mu dynamic, Young's modulus or the modulus of elasticity dynamic has been estimated. So, two frequency method gives mu dynamic as below. So, mu dynamic F1 is first longitudinal resonance frequency in hertz, F2 is the second longitudinal resonance frequency in hertz. A1, B1, C1 are constants based on dimensions of the cylinder. Once I know mu dynamic, then I can find E dynamic using this equation. Where E dynamic is dynamic modulus of elasticity, rho is the mass density of the material, F1 is the first longitudinal resonance frequency in hertz, R0 is the radius of the cylindrical specimen, and Fn is given by where A2, B2, C2 are constants based on the dimensions of the cylinder given by Subramanian et al. So, as a summary, it is seen that static modulus of elasticity, a simply modulus of elasticity, is about 0.83 of dynamic. That is one equation. The other equation says this can be also equal to minus 19, both are given by Neville 1997. So, one can see that if you are using static modulus of elasticity or simply modulus of elasticity in your calculations for the design or analysis, you are actually underestimating the capacity, because the modulus of elasticity of the material varies depending upon the shape of the material actually being used, and the dimensions of the cylinder of the material, and the loading methodology. Okay. So, one should strictly use dynamic modulus of elasticity in my estimating the parameters of the design, where we are using static values. So, this is one important uncertainty which comes from group number 2, which influences on group number 1 on a specific type of uncertainty, which is an important parameter in reliability studies. Okay. So, it is very important that we must know what is the variation approximately which compares the modulus of elasticity with that to the dynamic modulus of elasticity. Okay, there is a variation. Having understood this, let us now talk about formulation of a reliability problem. How do you formulate a reliability problem? Formulation can be broadly done in two ways. One, a time invariant problem. Two, a time variant problem. In both the cases, limit state function are defined which could be based on either limit state of serviceability or limit state of collapse, either way. So, the main objective of reliability problem is seeks to find the probability of failure of the system or probability of exceedance of the limit state. Let us talk about time invariant problem. If g of x denotes the limit state function and x denotes the set of random variables x1, x2, xn, then g of x less than or equal to 0 denotes the failure event. The probability of failure is given by Pf is the probability of g of x less than or equal to x, which is nothing but integral of f of x over the domain D dx. I call the equation number, is it 5? 7, where f of x is the probability density function since x is having combination of x1, x2, x3, I can say even this as joint probability density function of g of x equals 0. We can plot this. Now reliability will be given by 1 minus probability of failure. Let us say I can plot this domain. Let us say x1, g of x1, x2 equals 0. So, this is x1 and x2. I am plotting in a 2-dimensional domain. This is my failure domain. Anything outside the domain is a failure. So, this is a safe domain. So, you must integrate the joint probability density function over this domain. That is one of the kind of uncertainty. Okay, it is very complex. That is why it cannot be accurate. Let us talk about time invariant problem. Sorry, time variant problem. Now, the dependency of time will also need to be established in this kind of reliability problems. A reliability problem is said to be time variant if the limit state function is also a function of time. So, now the limit state function is g of x and y of t also. Okay, there is a time variancy, time dependency is also there. Where x1, x2, x3 are set of random variables and y of t is the vector of stochastic process. Now, if I try to plot this failure as y2 and y1, and this becomes my limit boundary, failure is expressed as outcrossing the boundary, or I should say outcrossing the limit boundary. So, this is a failure surface. Okay. So, my failure surface is outcrossed, I consider that event as a failure event. So, probability of failure is based on outcrossing of the vector y of t. Through the limit surface g of x comma y. So, probability of failure is now given by integral 0 t less than t of probability of minimum g x y of t less than 0 given x for any given value of x into f of x dx. Equation number, what is the number here? Here in this expression capital T denotes the lifetime of the structure. And of course f of x dx denotes the probability density function of the variable. We stop here, we will discuss this in the next class as an extension of the time variant problem. Any questions? Thanks.